Activity 9A, vector calculations. Number 1, just look up the answer in the back of the book. Number 2, write the equivalent bearing angle for 40 degrees south of east. Now, this is something we use all the time in physics. Let's have a look. Let's draw a compass where we've got north at the top. We usually indicate with an arrow. We've got east over here, no arrow, south here, and west there. And when we look at this compass and we use a protractor, we come around here 90 degrees from north to east. We come round all the way to south, 180 degrees. If we come all the way around to west, we've done 270 degrees. We've turned through 270 degrees, and of course if we rotate all the way around and back to where we started from again, we've done 360 degrees. And we'll use this all the time in physics. So 2, part A, write the equivalent bearing for an angle 40 degrees south of east. So we've got east, that's 90 degrees, and we've got a line which is 40 degrees south of east, so that's about here. So what is the bearing? If this is 40 degrees here, the bearing must be 90 plus 40 is 130 degrees. 2A. 2B, what if we've got north 56 degrees east? North 56 degrees east, we've got north, but we've come round 56 degrees east. North but 56 degrees east, that's about this here. North 56 degrees east, so that is a bearing of 56 degrees. And we just write 56 degrees just as we wrote 130 there. Okay, part C. What is west 30 degrees south? So west 30 degrees south. West, but 30 degrees south of west. West 30 degrees south, that's about there. So what is this angle here? This angle here is 270 minus 30 is a bearing of 240 degrees. Part D, 80 degrees north of west. So let's have a look at this then. 80 degrees north of west. Here is west, and we're 80 degrees north. It's going to be somewhere up here. So what is the bearing for this all the way around to here? It's going to be 270 plus 80 is 350 degrees. A bearing of 350 degrees. Number 3, we've got two force vectors. We've got A and we've got B. Draw a vector that represents vector A plus vector B. So vector A, head to tail, add to vector B. So the resultant of that is this vector here from tail to head. Resultant A plus B. 3A, 3B. Draw a force vector that could act together with A to produce B. So if we start out with this vector A, what would I have to add to this vector to get that vector? So let's draw that, shall we? This vector A plus something is equal to this vector B. This vector plus this vector must equal this vector. 3b. Number 4, a cyclist travels 2.5 kilometers east, 2.5 kilometers east, and then 10 kilometers south, 10 kilometers south, 10 kilometers south. Haven't drawn it well to scale. Let's do it better to scale. 2.5 kilometers east, 2.5 kilometers, remember east is over here, 2.5 kilometers east, 10 kilometers south, and finally 5 kilometers west. 5 kilometers west. Determine the cyclist's overall displacement from the starting point. Remember, distance is how far they've actually gone. Displacement is how far they are from where they started. So let's draw the vector for displacement. There's our vector for displacement, and we want to determine what this vector is. So we're going to have a magnitude, and we're going to have a direction for this. So let's complete this diagram, shall we? The length from here to here is 10 kilometers, and the length from here to here, 2.55, this length here must be 2.5 kilometers. So now we've got a triangle. It's a right angle triangle, one side 10 kilometers, this side 2.5 kilometers. So we can now use Pythagoras to calculate this length here, and if we use Pythagoras on that, we'll get this is 10.3 kilometers, 10.3 kilometers, and then we will use some trigonometry to find this angle here, and we'll come up with this angle is 14 degrees. So what's the displacement? The displacement is 14 degrees west of south, so that's a bearing of 180 plus 14 is 194 degrees, a bearing of 194, and a distance of 10.3 kilometers. Okay, number 5, we've got this object here, an object which has got 4 forces applied to it, 4 newtons this way, 2 newtons down, 6 newtons to the right, 4 newtons upwards, and we're to determine the direction of the resultant force. So we've got 2 newtons down, we've got 4 newtons to the left, we've got 4 newtons up, and we've got 6 newtons to the right. So the resultant of all of those has got to be this here. So this is the resultant force on this object when we add these 4 forces head to tail. And we can quickly see if this is 6 along the top, 4 this way, this has got to be 2 newtons from here to here, and 2 down and 4 up. This has got to be 2 newtons up there, so that will give us a right angle triangle with sides 2, so that means this must be 45 degrees. So that's our resultant force. We could have done it another way. We could have said we've got 6 newtons this way, 6 newtons this way, and 4 newtons to the left. That's a total of 2 newtons to the right, and then looking at the vertical forces, we've got a force down of 2 newtons and a force upwards of 4 newtons. If we add these two together, the resultant will be 2 newtons up So we've got 2 newtons to the right, 2 newtons up, 2 newtons to the right, 2 newtons up, and the resultant of that will be again the same force here at 45 degrees. Number 6. Number 6. A bird flies 3 kilometers to the west. Remember this. North, east, south and west. A bird flies 3 kilometers to the west. 3 kilometers, it's our birdie flying. And 4 kilometers to the south. 4 kilometers to the south. Find the resultant displacement. So initially the bird was displaced 3 kilometers in this direction, displaced 4 kilometers in this direction. So the overall displacement of this bird is represented by this vector here. So we need to find a magnitude and we need to find a direction. The magnitude, because it's a right angle triangle, we can use Pythagoras, and let's do a Pythagoras for this, shall we? Pythagoras is this side squared plus this side squared is equal to this side squared. So let's call that the resultant, and we will say 3 squared, Pythagoras, 3 squared plus 4 squared is equal to r squared. This squared plus this squared equals this squared. 3 3s are 9, 4 4s are 16, 9 plus 4, 9 plus 16 equals r squared. 9 plus 16, 25 is equal to r squared. R must equal 5. So the length of this side is 5 kilometers. We can say the bird is now displaced 5 kilometers from where it started. And let's find this angle here. We're going to look at that more in the next video. But quite simply, to find this angle theta, we could use tangent or sine or cos. Let's use sine. Sine of theta is equal to opposite over hypotenuse is equal to 4 over 5. Therefore, theta is equal to inverse sine 4 over 5.8. Therefore, theta is equal to 54 degrees. This angle is 54 degrees. So let's have a look from at our bearing. That's north. This is 270 minus 54, which means that is a bearing of, wait, 53 degrees. So that's a bearing of 270 minus 53, which is a bearing of 217 degrees. We can say that the bird is displaced 10.3 kilometers at a bearing of 194 degrees. Okay, I've missed number 7 out, just moved on to number 8. Remember this again. Here is our bearings. North is 0 degrees, 10, 20, 30, 40, 60, 90, 180 degrees, 270, and back around to 360. Number 8, a velocity of 30 kilometers per hour, 30 kilometers per hour west is added to another velocity vector 20 kilometers per hour north, 20 kilometers per hour north. These two vectors are added. Use a vector diagram to determine the magnitude and direction of the resultant. So add these two together, head to tail, and the resultant vector is this vector here, and we're asked to find the magnitude and direction of the resultant. So again, to find the resultant vector, we use Pythagoras. So a squared plus b squared equals c squared. 20 squared plus 30 squared is equal to r squared. Therefore 400 plus 900 is equal to r squared. Therefore r, work it out for yourself, is equal to 50 kilometers per hour. That's probably a triangle that you remember. No, it isn't. Sorry, I've got it wrong. Made a mistake. 20, 30, I've done 20 plus 30 is equal to r squared. R squared is equal to 1300. Therefore r is equal to 36 kilometers per hour. And again, remember our units. And now we need to work out this angle here from our triangle. Let's call it theta. We can use our, let's use a tangent. Tangent is opposite over adjacent. We can use tangent theta is equal to opposite over adjacent, 20 over 30. Therefore theta is equal to the inverse tan of 2/3, 0.667. Therefore theta is equal to, let's look at this, inverse tan 0.667, inverse tan 0.667 equals 33.7 degrees. So let's work that out as a bearing. It's 270 plus 33.7 is a bearing of 304 degrees. So there's our displacement vector, 36 kilometers per hour at a bearing of 304 degrees. Number 9, we have this vector here, and we're asked to find what is the vertical component, horizontal component, and the vector. So let's look at the vertical component of this vector. You're beginning to look at the vertical components and horizontal components. Any vector can be considered the resultant of two or more vectors. So if we have a vector like this, we could say that's the resultant of this vector plus this vector plus this vector plus this vector plus this vector. This vector is the resultant of all of those. Or we could say this vector is a resultant of this vector plus this vector. Two vectors to produce that resultant. In particular, when we're looking at a particular vector, we want to look at the two vectors which make it up, one of them being horizontal and one of them being vertical. So we will say this vector, horizontal vector, plus this vector, vertical vector, is equal to this resultant vector. And so we see in this diagram here, we can have these two vectors. We can have this vector, a horizontal vector, plus this vector, a vertical vector, together add up to make this one resultant vector. And this is called the horizontal component of the vector, horizontal component of the vector, and this vector is the vertical component of the vector. So question A is, what is the vertical component of this vector? We need to find this length here. So to find this length here, we can just read it off. It is 3 units. So the vertical component is 3.0 b. What is the horizontal component horizontal component is this vector here, which is a length of 4, and see what is this length here. And again, we can use Pythagoras. If we know this side plus this side, we can use Pythagoras. Which is a squared plus b squared equals c squared, the hypotenuse. The two smaller sides and the hypotenuse. This squared plus this squared equals that squared. So we have 4 squared plus 3 squared is equal to c squared, and we do our sums, and that's going to equal 5.0 units. Components. For this vector, we can say it's a resultant of this vector plus this vector, this being the horizontal component, the vertical component adds up to that. Number 10, two component forces, 4 newtons upwards and 6 newtons horizontally act together on the same object. Find the resultant force by drawing a scale vector diagram. So here's my object here, and we've got two forces, 4 newtons vertically upwards. So let's do a scale diagram, 4 newtons. I'm going to use centimeters for this. 4 newtons, scale diagram, that's 4 units long, 4 newtons upwards, and 6 newtons horizontally act on the same object. So we've got another object, another force, 6 newtons acting on the same object. 6 newtons. Find the resultant force by drawing a scale vector diagram. Okay, so we can say this vector plus this vector, so let's have it, and this is at a right angle, plus this vector 6 this way, at exact right angle, 6 this way. This vector plus this vector is equal to this vector here. Because it's a scale diagram, we can actually read off the length because we've drawn it very carefully, and our length is 7.1 Newton, and we bring our protractor, and I don't have a protractor at home, but if we bring our protractor we can measure this angle here, and that angle we'll measure it out to be approximately 55-56 degrees, and again we can have a bearing on this of 56 degrees, but because it's an object, just make it clear that that'll be 56 degrees. Number 11 is one of my favorite ones, again, the change of velocity. So we've got a vector here which represents the initial velocity, v initial, and we've got the second vector, b, which represents the final velocity, and we have to draw a vector representing the change of velocity. Remember our thinking on this, our formula, the change of velocity is equal to the final velocity minus the initial velocity. And to help us draw our diagrams, we say that's the same as saying final velocity plus the negative of the initial velocity. So change of velocity is equal to final velocity plus the negative of initial velocity. If this is the initial velocity, then this vector here must represent the negative of the initial velocity. Same size, opposite direction. So let's now have final velocity plus the negative velocity there. So we've got final velocity plus the negative of this velocity must be the change of velocity. This here is the change of velocity. Okay, question number 12. We've got a soccer ball travelling at 5 meters per second. 5 meters per second. It hits the crossbar of the football goals and then comes back directly in the same direction at 4 meters per second, opposite direction. Determine the ball's change of velocity. Change of velocity is equal to final velocity minus initial velocity, and we write it as the final velocity plus the negative of the initial velocity. So let's calculate the change of velocity. First of all, we need to make sure that we know which of these numbers are positive and which are negative. Let's consider this direction as being the positive direction. That means the ball is initially kicked at 5 meters per second in this direction, so it's got a positive velocity. When it hits the crossbar and rebounds, it's going back this way, so this has a negative velocity. We've got to get those right for a start. So let's then have a look. Change of velocity is final velocity plus negative of the initial velocity. The final velocity is negative 4 meters per second plus the negative of the initial velocity plus the negative of this. If this is the initial velocity, the negative of that is the same line in the opposite direction. It must be negative 5 plus the negative of 5. Negative 4 plus negative 5 is equal to negative 9 units meters per second. And we've got to indicate then what this direction is. This sign gives us the direction. This is positive, negative in this direction, so this is 9 meters per second in a direction away from the crossbar. Question 13. A car travelling east at 40 kilometers per hour. 40 kilometers per hour east. Here's our north, east. And it's clearly an SUV travelling 40 kilometers per hour, turns a 90-degree corner and ends up travelling north at 20 kilometers per hour. 20 kilometers per hour travelling north. Find the car's change in velocity in both magnitude and direction. Change of velocity is equal to final velocity plus the negative of the initial velocity. So let's have a look. If this is the initial velocity, a vector this length in this direction, then this one here must be the negative of the initial velocity. Same size, opposite direction. So let's add these two up as vectors. We've got the final velocity, 20 kilometers per hour. And we've got the negative of the initial velocity, 40 kilometers per hour. So the resultant, the change of velocity, is this vector length here. And we need to calculate the magnitude and direction of this vector. Again, using Pythagoras, a squared plus b squared equals c squared. We can see the magnitude is equal to 44.7 kilometers per hour. And the direction, let's look at this direction. Let's look at this angle here. And let's use the tangent. And we'll say tangent of theta is equal to opposite over adjacent is equal to 40 divided by 20. So the inverse, the theta is equal to the inverse tan of 2, which is equal to inverse tan of 2 is equal to 63.4 degrees. So if we are going to give that a bearing, we will say 360 minus 63.4, the bearing is equal to 297 degrees. So that's the magnitude and direction of that change of velocity for that vehicle. A tennis ball is thrown against a wall and rebounds without a loss of speed. Draw a scale vector diagram to find the direction of the ball's change in velocity. So we're given that the tennis ball comes in and strikes this wall at 50 degrees, and it rebounds, and traveling at 6 meters per second, and it rebounds also at 6 meters per second and also at 50 degrees. And we're asked to draw a scale vector diagram to find the direction of the ball's change of velocity. Change of velocity is equal to initial velocity final velocity minus initial velocity. It's final velocity plus the negative of the initial velocity. So let's see, we've got our final velocity here, and we've got our initial velocity here. The negative of the initial velocity is here, so let's do our addition. Final velocity which is 6 meters per second, and let's do it to scale. 6 to scale. Final velocity, let's add the negative 6 in this direction, getting our angles right. Negative of the initial velocity, and so the resultant has got to be this line here, which if we've drawn it correctly, which we have exactly, it'll be in this direction here. So draw a scale vector diagram to find the direction of the ball's change in velocity. That's there, and we can do some simple sums to see what that angle is there. So that's that section, and look for the next video. We're going to look at some of the problem sheets, some of the worksheets that Ms. Blackwell has handed out. Thanks guys.